As we know, there are different types of central limit theorems. That means some theorems that actually ensures the convergence in distribution. One such theorem is Lindbergh-Levy theorem, and we also know Lyapunov's CLT. Today we will discuss another such theorem, which is known as a Lindbergh-Feller CLT. So Lindbergh-Feller CLT is basically based on some assumptions, and these assumptions actually are only up to the existence of up to the second order moment. So as we have already seen that Lyapunov's CLT requires existence of moments slightly higher than second order, but Lindbergh and Feller is in that sense slightly weaker in the sense that it requires not really very higher order existence of not very higher order moments. So we will actually discuss the proof in detail about this CLT. Although initially we will start with a mention of previous other two theorems, namely Lindbergh-Levy theorem and Lyapunov's CLT. We are discussing some more theorems on central limit theorems or convergence in this that deals with convergence in distributions. First one we have already shown previously, the Lindbergh-Levy theorem, which deals with a sequence of IID random variables under the existence of second order moment. Then we know there is another theorem, central limit theorem, known as Lyapunov's CLT, which says that if xn is a sequence of independent random variables such that expectation of xk equals to 0, expectation of xk square equals to sigma k square less than infinity, and we define small sn as summation sigma k square k equals to 1 to n, and we assume that the existence of slightly higher order moments of slightly higher than 2, which is summation k equals to 1 to n expectation of mod xk to the power 2 plus delta by Sn to the power 2 plus delta, this goes to 0. That means this is known as Lyapunov's condition for 0 less than delta less than equals to 1. Then capital Sn, that is the sum of random variables, sum of xi is x1 x2 xn by Sn converges in distribution to tau, where tau follows normal 0 1 as n goes to infinity. Now one important thing is that Lyapunov's CLT requires moments of higher order than those figured in the formulation of the problem. In the formulation of the problem, we see that sigma is there, but it requires existence of moments of order higher than the second one, that is higher than sigma square. So Lindbergh in 1928 proved another CLT for independent random variables, for which Lyapunov's condition of finiteness of more than second order moments is not really necessary. There is another slightly weaker condition for this. Feller in 1936 proved that Lindbergh's condition is also necessary and for CLT and for negligibility of individual contribution of variance of the random variables corresponding to the total variance. That means this Lindbergh's condition is necessary, and it will ensure that the individual contribution or the contribution of the variance for individual variables is really small compared to the total variance. So let us prove Lindbergh-Feller theorem. Here also we assume that xn is a sequence of independent random variables only, and we are not assuming that they are identically distributed. So unlike the assumption of only independence, we also assume that expectation of xk equals to 0, expectation of xk square equals to sigma k square less than infinity, and Sn equals to variance of capital Sn, which is equals to summation k equals to 1 to n sigma k square. Under this, then capital Sn, that is the sum of random variables x1 x2 xn divided by small sn, converges in distribution to tau, and maximum over k lies between 1 and n of sigma k by Sn, this goes to 0 as n goes to infinity, if and only if for every epsilon greater than 0 and fk being the distribution function of xk, if we have Gn epsilon, which is Sn to the power minus 2 summation k equals to 1 to n integration over mod x greater than equals to epsilon Sn x square dfk. This goes to 0 as n goes to infinity. That means we are defining a function that depends on epsilon and obviously on each of the distribution function, that means distribution function of each of the random variables. This function, this particular function goes to 0 as n goes to infinity, and this is a necessary and sufficient condition for the existence of this CLT or this type of convergence of Sn by small sn. A couple of important notes that condition 1 is called Fellers condition and condition 2 is called Lindbergh's condition. Condition 2 is called Lindbergh's condition and Gn epsilon is called Lindbergh's function. Now, if we define Gn star epsilon, which is Sn to the power minus 2 summation k equals to 1 to n integration mod x less than epsilon Sn. Now, remember previously in Gn epsilon, this quantity, this set on which we are considering the integral is mod of x greater than equals to epsilon Sn. Now, we are just taking the complement of this set, and over this set we are considering the integral of x square df with respect to fk. This quantity, that means Gn epsilon star, goes to 1 as n goes to infinity. In fact, this is equivalent to the condition 2. So, let us consider the proof. First, we will show that Lindbergh's condition implies Fellers condition. Let us start with sigma square, as we know that sigma k square, which is variance of xk, always plays a very important role in most of the central limit theorems. So, sigma k square equals to integration x square over with respect to fk, that is dfk, because expectation of xk is 0 for every k, we have assumed that. Now, we split the integral into two different sets. One is complement of the other, that is integral over mod x less than epsilon Sn x square dfk plus integral over mod x greater than equals to epsilon Sn x square dfk. Now, if we replace mod x by epsilon Sn, the first integral is less than equals to epsilon square Sn square, and the second, let's keep second as it is. Then, if we consider sigma k square by Sn square and take maximum over k lies between 1 and n, we can immediately write this is less than equals to epsilon square plus Sn to the power minus 2 summation k equals to 1 to n integral over mod x greater than equals to epsilon Sn x square dfk. Now, the left side in the inequality is nothing but Fellers condition, and the second term in the right side is basically Lindbergh's condition. Since we have assumed that Lindbergh's condition holds true, then the second term goes to 0 as n goes to infinity and epsilon is arbitrary. So, Fellers condition is satisfied. Now, consider epsilon greater than 0 and Gn epsilon goes to 0 as n goes to infinity. So, that means we are assuming that Lindbergh's condition holds true now. So, it is possible to choose epsilon n, a sequence of epsilon n's goes to 0 as n goes to infinity, such that epsilon n to the power minus 2 Gn epsilon n goes to 0 and epsilon n to the power minus 1 Gn epsilon n goes to 0 as n goes to infinity. Again, define a new random variable denoted by xnk, which is equals to xk into indicator function over mod x less than epsilon n Sn, and we define Snn in terms of xnk, that is Snn is summation k equals to 1 to n xnk. Then consider the probability that Snn by small sn not equals to Sn by small sn, which is naturally less than equals to summation k equals to 1 to n probability xnk not equals to xk, which is equals to, we can immediately see, which is equals to summation k equals to 1 to n integral over mod x greater than equals to epsilon Sn. because as long as mod x less than epsilon n Sn, xk and xnk are equal, that is by the definition of xnk. So on the set mod x greater than epsilon n Sn, these two differs. So we are considering integral only on this set. Now again this quantity is less than equals to epsilon n Sn to the power minus 2 summation k equals to 1 to n integral mod x greater than equals to epsilon n Sn x square dfk, just by simple algebra, which is equals to epsilon n to the power minus 2 into gn epsilon n, that is by the definition of gn epsilon n, and naturally this goes to 0 as n goes to infinity. So what we get here is that probability Snn by small sn not equals to Sn by small sn goes to 0 as n goes to infinity. This immediately implies that Snn by small sn and Sn by small sn are tail equivalent, and hence they have the same limit in law as n goes to infinity. So in order to show that Sn by small sn goes to tau in distribution, it is enough to show that Snn by small sn goes to tau in distribution. So note that S small Snn square equals to variance of capital Snn, and we know that expectation of xk equals to 0. So we naturally have 0 less than equals to 1 minus Snn small Snn square by small n square, which is equals to variance of capital Sn minus summation k equals to 1 to n expectation of xnk square minus expectation square of xnk divided by, entire thing is divided by small sn square, which is equals to Sn to the power minus 2 summation k equals to 1 to n expectation of xk square minus expectation of xnk square plus Sn to the power minus 2 into summation k equals to 1 to n expectation square of xnk. So we are just doing little bit of algebra here, which is equals to Sn to the power minus 2 summation k equals to 1 to n integral mod x greater than equals to epsilon n Sn x square dfk plus Sn to the power minus 2 summation k equals to 1 to n expectation square of xnk. Now the first term is nothing but gn epsilon, and second term is applying the definition of xnk, which is defined over the set mod x greater than equals to epsilon n Sn. The second term is Sn to the power minus 2 summation k equals to 1 to n modulus of integral mod x greater than equals to epsilon n Sn x dfk square, which is equals to, which is less than equals to gn epsilon n plus Sn to the power minus 2 summation k equals to 1 to n integral mod x greater than equals to epsilon n Sn x square dfk, and again this goes to 0 as n goes to infinity. So here we have that small Snn by small Sn goes to 1 as n goes to infinity. So therefore, so initially we are trying to prove that capital Sn by small sn goes to tau in distribution. Now we have shown that small Sn by small sn goes to 1 as goes to infinity. So naturally it is enough to show that capital Sn by small sn goes to tau in distribution. And again, since we know Lyapunov's CLT, we will just show that Lyapunov's condition is satisfied in this case, and then we are through, because we can directly apply Lyapunov's CLT. Now note that modulus of xnk minus expectation of xnk is less than equals to 2 epsilon n Sn. Now as epsilon n goes to 0, Snn to the power minus 3 summation k equals to 1 to n expectation of mod xnk minus expectation of xnk modulus of the entire quantity whole to the power 3, which is less than equals to 2 epsilon n Sn into Snn to the power minus 3 summation k equals to 1 to n expectation of xnk minus expectation of xnk whole square. Just by doing little bit of algebra, we can immediately show that this quantity is less than equals to 2 epsilon n Sn into Snn to the power minus 1, which goes to 0 as n goes to infinity. And so we have the proof, because the Lyapunov's condition is satisfied, so we just apply Lyapunov's CLT and the proof follows immediately. Now we have to show Phillips condition and CLT implies Lindbergh's condition. We know that if we consider the characteristic function, then we know that modulus of phi k t by Sn minus 1 is modulus of this quantity less than equals to t square by 2 into sigma k square Sn to the power minus 2. And Phillips condition implies that maximum over k lies between 1 and n, modulus of phi k t by Sn minus 1 goes to 0, because maximum over sigma k square by Sn square goes to 0 as n goes to infinity. Also, summation k equals to 1 to n modulus of phi k t by Sn minus 1 whole square less than equals to, just take one term outside, maximum over k lies between 1 and n modulus of phi k t by Sn minus 1 into summation k equals to 1 to n modulus of phi k t by Sn minus 1. And doing again little bit of algebra, we can show that this entire quantity is less than equals to t to the power 4 by 4 into maximum over k lies between 1 and n, maximum of sigma k by Sn square, and by Phillips condition this goes to 0 as n goes to infinity. So by equation 3 we can immediately write that modulus of phi k t by Sn minus 1 is less than delta for n greater than equals to n naught. N naught is very large and k less than equals to n. Hence, using all the arguments we have just discussed here, we have summation k equals to 1 to n modulus of log of phi k t by Sn minus phi k t by Sn minus 1 less than equals to summation k equals to 1 to n modulus of phi k t by Sn minus 1 square, which is equals to small o of 1. Just now we have shown this by Phillips condition, this goes to 0. So as n tends to infinity. So we also know that CLT holds. So what is the meaning that CLT holds? That means product k equals to 1 to n phi k t by xn goes to e to the power minus t square by 2. So if we take log on both sides, we see that summation k equals to 1 to n log of phi k t by Sn goes to minus t square by 2. So it is immediate that minus t square by 2 is nothing but summation k equals to 1 to n phi k t by Sn minus 1 plus small o of 1. Let us call it equation 4. Now we again do standard algebra, just equate real parts on both sides of equation 4 and doing little bit of manipulation, we get that the last one, that is summation k equals to 1 to n integral mod x less than epsilon Sn into 1 minus epsilon Sn of integral of 1 minus cos tx by Sn dfk. Now, here also we have applied that particular technique, that splitting a particular set into two sets, one is the complement of the other, and doing little bit of manipulation we have this quantity that half t squared gn epsilon plus small o of 1, that means this second term goes to 0, less than equals to summation k equals to 1 to n integral over mod x greater than equals to epsilon Sn of 1 minus cos tx by Sn dfk. This entire quantity is less than equals to 2 into summation k equals to 1 to n integral of mod x greater than equals to epsilon Sn dfk, that is less than equals to twice epsilon Sn to the power minus 2 into summation k equals to 1 to n integral of x square dfk. That means we are introducing x square inside the integral, and for that we adjust this by epsilon Sn, but we are getting an inequality in between because of the restriction that mod x greater than equals to epsilon Sn. So ultimately this entire integral is nothing but twice epsilon to the power minus 2 into gn epsilon. Now if we choose T is less than equals to 4 by epsilon, then it is clear that epsilon to the power minus 2 is into Gn epsilon equals to small o of 1 for every epsilon greater than 0. So it is immediately clear that Gn epsilon goes to 0, because here we have fixed epsilon as n goes to infinity for every epsilon greater than 0. So it is clear that Fellow's condition and CLT jointly together they implies Lindbergh's condition, and hence the proof of Lindbergh-Feller CLT is complete. Thus Lindbergh-Feller CLT is really an important important CLT, and this really ensures convergence in distribution of the sum of random variables under some specific conditions. But one important thing that I wish to point out, that if you look at the proofs of this theorem and look at the technique of this proof, here we have used many times like splitting one event into a particular one part of the event and its complement, and we deal separately these two parts and then merge these two things to get the final result. So this is a very common technique, and here we have used this many times to see how it works, and incidentally it really works nice, and the proof becomes very elegant just by applying this technique. And we have also used the characteristic function, because we know that there is one theorem called inversion theorem of characteristic function, and also uniqueness property of characteristic function ensures the convergence. So here we have used many things that we have already learned in the measure theory and in probability theory. So this thing we should, and many things are coming from real analysis knowledge. So Lindbergh-Feller theorem is a very important one that encompasses all sorts of things, techniques. The technique is very useful, and we can use this technique in many other problems. So that is the main thing that I want to point out.